All right, so all of us dream of doing work that illuminates and points a broad research direction that will lead to a lot of success, and to do like fundamental work at the methodological level and have real application-oriented success. And Hoifung is one of my favorite examples of somebody who's done wonderful work in all three of these dimensions. Now one of the major trends in research is massive unsupervised pre-training. And 10 years ago, Hoifung won a Best Paper Award for work on unsupervised semantic parsing. A little bit after that, he also did work, some fundamental methodological work on some product networks. But really, his main focus over these last many years has been applying machine learning to precision medicine. And it's just through kind of dogged persistence and intellectual creativity that he's having great impact. And I'm so happy that he's here.
Thanks a lot for Andrew for the very kind introduction. I'm very excited to be part of this new conference. So looking forward to talking to all of you in the next few days. I'm fully aware that I'm between you and the lunch, so hopefully you can make the wait worthwhile. So I will start by introducing precision medicine and why this is such an exciting area to get into right now, and also more importantly for this crowd, why NLP and in particular machine reading could play a key role in this emerging area. I would then explain, as Andrew mentioned, the challenge of lacking label example in such a high-value, sort of specialized domain, and our long-standing research agenda in how to basically leverage prior knowledge as free lunch to as indirect supervision or self-supervision to kind of overcome this this bottleneck. And finally, I would talk, discuss a little bit about this emerging area of curation-as-a-service, where machine reading can potentially help save life, cut costs, and make drug development sustainable. So in the ideal world, you want every patient to respond to the treatment they are prescribed to, as represented by the blue person here under each drug, right? In the real world, unfortunately, actually oftentimes the patient do not respond to the drug, as signified by the red here. And in fact, if you look at the top 20 drugs in the US by gross sale, 80% of it's estimated 80% of them don't respond to it. So this is a very bad 80-20 rule, right? So, I mean, this is a well-known problem in medicine, and the doctors are obviously a very smart bunch. The challenge, however, is used to be we don't have sufficient sort of feature to distinguish between the red and blue, right? So the advent of big data in medicine actually promised a change for the good, right? So cancer is the poster child of this, right? 20 years ago, at the conclusion of Human Genome Project, it took billions of dollars, tens of countries, and over a decade to sequence a couple of human genomes. Now you can basically train a high schooler to do this in a couple of days for the cost of under $1,000. We're actually quickly approaching 100, right? And cancer, from cancer biology, we know that by the time the tumor is formed, it's completely driven by the genetic mutation. So you're literally, with the cancer genome, you're literally staring at the source code of the cancer. So in principle, you can differentiate all those blue and the red down to the individual level, right? The challenge, however, is that big data also create this sort of like canonical challenge of information overload, right? So for example, now all of a sudden we have all the genes in our genome which have 20,000 genes, and there are millions of observed variants. And also in cancer, there are exploding of drugs in targeted drug, immunotherapies, and so forth. There are now thousands of them either approved or in the pipeline. So when you're oncology trying to make a decision to save a patient's life, you now have this huge, gigantic space of combinatorial explosion, and you need to know a lot about how those genes, like those mutated genes, what do they originally do? Are the mutation actually functional? What are they doing here in the cancer? And also, crucially, what drug might be able to use against the tumor, right? So to make the discussion concrete, let's look at sort of a key representative scenario called the molecular tumor board, right? So basically nowadays, when you got all this cancer genome, right? Here is 500 mutated gene for this cancer patient. So what do we do about it? Essentially, people basically assembly, convene a bunch of specialists in the war room, right? Try to do manual divide and conquer, right? The challenge of this obviously is not scalable. There are, in the US alone, there are 1.7 million new cancer patients every year. Globally, there are 8 million, and the number is actually rising as population age more and more. In big cancer centers like Memorial, they already begin sequencing everybody, but their tumor board actually only have the capacity to actually review a fraction, tiny fraction of those cases, right? And you can argue, even if we have infinite number of oncologists, the sheer economic cost is really not, we are not going to make it. So one of the big bottleneck for this tumor board guys is that they need to basically keep track of all those exploding knowledge between the drug, the gene, the mutation, and the cancer types, etc. So obviously, the first thing you do is to hire people, hire experts to try to throw money at the problem, right? So here's the team at Memorial. They basically, their full-time job is to look at the PubMed paper, try to curate all those available information so that they can be at the fingertip of the tumor board. Now, the challenge for these guys, obviously, is that they are really reading from a fire hose, right? So every minute I'm talking here, there are 2 new papers pop up in PubMed. Every day there are 4,000 of them. Every year there are 1 million, right? And if you ask a curator, expert curator, how many papers do they curate, it's probably 4 or 5, right? So that's sort of like motivating our research agenda in Project Hanover, where we are kind of focusing on trying to develop machine reading technology to try to help this expert accelerate their curation process to actually unlock those valuable information that could mean life and death in the decision making. So for example, given a piece of text in the PubMed, it may start by describing a patient cohort with this EGFR gene and mutation LA150A, and then later on it reported that we fed this guy this new drug, gefitinib, and then it seemed to be working partially, right? So from a pure tumor board point of view, you want the machine reader to be able to find those this kind of facts to describing the drug response, the relation between the drug response and a particular genetic composition in the tumor, and they could be very valuable. And so our aspiration is that can we enable those curators to curate much faster, right? So obviously, if you can develop machine reader technology to do this, then there is hope in that. But as we all know, there are lots of challenges in natural language understanding, right? So the first challenge, as we all well know, is that people are very creative in figuring out different ways to say the same thing, right? So here, just a few ways to say that this tumor suppressor, P53, can inhibit the apoptosis pathway BCL2. And if you look at the small corpus of a few hundred abstracts, there are already a long tail of different words describing this kind of negative regulations, right? Now, on the flip side of that, the same expression can also refer to very different things, right? So, and one of the fun things in medicine is that you actually have a gene called PDF. And so now if you are a machine reader, you must be scratching your head like whether this is a text format, a gene, or maybe probability density function or something, right? And also, as Wally alluded to, right, so there has been, we have been kind of making lots of progress in sentence level, for example, or binary relation extraction. But when you go to important specialized area like biomedicine, that's not sufficient, right? So for example, the piece of text might be, what you want to get from this piece of text is that this drug actually can be potentially applicable to the gene ALK with a particular mutation, right? But actually, the gene was mentioned early on in the paper and never mentioned again, all right, when you are describing the relation between the drug and the mutation. So now, in order to extract this kind of N-ary relation, you need to actually really go expand your scope to the full document level and the N-ary relation. So that would pose a lot of novel challenges. So obviously, we have a very powerful tool to deal with those variation, ambiguity, and so forth, right? So deep learning is sort of the new toolkits that add to our ammunition. But just like any other standards or supervised learning methodology, the challenge, the sort of the Achilles heel is that we need to feed them many, many label examples, right? So in the general area, you can, there are many fascinating work in like how do you crowdsource those examples, so to bootstrap from there. In specialized domain like medicine, that is actually much harder to do, right? So imagining asking a Turker to help you parse a PubMed paper, interpreting a CT scan of a tumor, that's actually non-trivial. So a lot of our sort of focus over the years is to basically accept this premise that we are not going to have a flood of label example. So how do we deal with it, right? So in the real world, there is no magic. So we need to compensate. If we don't have sufficient label example, we have to compensate for the lack of it by pulling some sort of free lunch from somewhere. So we are kind of focusing on taking a lot of the sort of the structural resource in biomedicine and then leverage them for indirect supervision, or more recently, people call this self-supervision. And so one of the canonical examples that many of you is well aware of is distance supervision, right? So for example, because in biology, understanding how genes interact with each other is very important, right? So our cells are basically a bunch of if-then rules that one gene turn on, that will inhibit another gene, and so forth, right? So the National Cancer Institute basically mobilized a bunch of editors in the Nature publishing group to basically sit down, try to curate this kind of fact. So each line is one of the regulation between two genes. So they basically did this, curated a very high quality knowledge base with about 10,000 facts in 2 years. The problem is that after 2 years, all those editors quit because it is too labor intensive. So then the knowledge base basically quickly go obsolete and so forth. So if you stare around the biomedicine, there are literally hundreds of this kind of knowledge base, right? They basically, you got some funding for a few years, you curate it, and then after a while, you cannot sustain it, and then it go into oblivion. So our sort of like, one sort of like powerful learning paradigm is to try to basically leverage them to hallucinate sort of noisy label training data, all right? So for example, you can basically get infinite supply of unlabeled text, and now pretend for a second like you are a machine reader. You don't know what those words means, right? Like this are Russian, like you don't know what inhibits means, but you actually saw that the two genes actually appear in the same sentence, right? So the BCL2 and the P53, and you also know about this prior relation between these two genes. Then you can basically now hallucinate, hypothesize that this may be describing this relation, right? So obviously this already have been sort of like very powerful if out of blocks, right? To actually bootstrap a machine reader with binary relation within a sentence. The challenge now is like, how can we extend this to sort of a document level, N-ary relation extraction? And even in the binary sentence level case, there is a lot of noise, right? The two gene may appear for many other reasons. But what we can do is to actually mobilize other sort of the prior knowledge and other resource to actually help clamp down on the noise, right? So for example, a bunch of us sort of have been doing a lot of work in this joint inference where you're trying to leverage the interdependency of those independent sort of labeled decisions to try to clamp down the noise and amplify the signals, right? So when you look at the PDF at the beginning, there are 4 of them, and for each of them, you have no idea whether it's a gene, a DEX format, or whatever, right? But one thing you can leverage is that because they appear close by, they are likely to be co-referenced, right? So that's just a generic sort of linguistic heuristic. So now all of a sudden you reduce these 4 independent sort of uncertain decisions into a single one with high likelihood, right? Second thing you can leverage is this linguistic construct of apposition when you have peptide deformulase followed by the parentheses of PDF, which is how people usually describe acronym, which also means that those 2 expressions are likely to be co-referenced again, right? So, and then the third piece of information is because we have all this wonderful sort of ontology resource, structure resource in medicine, right? So people, you can actually easily find a resource that tell you all 20,000 genes, what are the canonical symbol, what are all the aliases, right? So peptide deformulase actually match one of the aliases, and unlike PDF, it's a much longer string, and therefore it's actually less ambiguous. So now if you combine all this sort of general knowledge apply into this particular instance, you can suddenly have a sort of high probability conclude that probably here the PDF actually is a gene reference. And then obviously you can also, instead of asking expert to, annotate individual examples, which is not very scalable, you can ask them to sit down for half an hour, think about the domain, and then write a bunch of rules, right? That's not too hard to do. And so that would also contribute sort of another source of sort of like prior knowledge you can combine. And of course, all these three types of knowledge and constraints and so forth, they are obviously not foolproof, right? But for many of us whose previous life is in this probabilistic logic or current life, right? And there is no problem with it, right? We can basically introduce logical formula to describe the constraint, but we attach sort of like weights or basically assign probabilistic meaning to them to model the uncertainty. And essentially, we are describing, define a probabilistic distribution over a lot of this sort of latent label examples, right? So each of this circle here, think about it as like whether this PDF is a gene or not, whether this paragraph describing this drug gene mutation decision or not. A priori, you don't know those label examples. If you know them, then it's just standard supervised learning. But what you can leverage from the prior knowledge is a lot of interdependency among those label decision making. And then you can basically using probabilistic logic to encode them. And now you can apply state-of-the-art probabilistic inference to actually come up with sort of like a modular distribution, which you can then view as sort of like essentially probabilistic labels. And now you can basically involve all your favorite, classification machinery like deep learning to basically treat those as probabilistic label and train your favorite deep neural network. So essentially, you can think about it as like we're leveraging those prior knowledge with probabilistic logic to kind of hallucinate a lot of those noisy probabilistic labels, and then using deep learning to actually capitalize on those labels, right? So for those of us who have battled with like probabilistic logic, macro logic before, we know that one of the big challenges is the scalability, right? So to actually have a full graphical model describing all the way down to the linguistic patterns, that is very quickly exploding, as Guy mentioned in the talk, right? So the idea here is that we can now actually have a sort of decomposition where probabilistic logic focus on the much smaller search space with those label decisions, latent label decision, and the prior knowledge, and then deep learning or whatever the next powerful tool can handle all those pattern, local pattern recognition and so forth. So we also try to explore a little bit to extend the latest sort of like neural architecture. For example, a lot of the standard sort of like recurrent neural network, LSTM and so forth, basically look at it, model the word sequence as a sequence, right? Like you have a linear chain of the modeling, and then your recurrent unit is basically focused on the previous word, right? However, if you look back in the NLP, we spent 2 decades in figuring out the best parser and other linguistic analysis and so forth. So the motivation here is that can we leverage all those sort of like linguistic structure to help actually speed up the learning in the recurrent neural network, right? So the idea is actually very simple, right? So we can extend the recurrent unit not just to the previous word, but to any previous sort of dependent words, right? So you now could have multiple sort of like precedents, and then you basically figure out, introduce a gate for each one of them. And essentially you can, another way to think about it is that this is essentially a hard attention, right? That bootstrapped by this linguistic structure. So there will be a very exciting sort of area. Can we also combine this with all this latest fascinating work in self-attention? As we mentioned earlier, it's kind of mandatory that we have to go to the document level relation extraction, but that means that if you apply something like that distance supervision or other technology naively, you will get an explosion of noise, right? So your signal will be completely crowd out. So there has been a lot of exciting work actually starting working in this area. For example, Paul Werger and Andrew and others in here have done amazing work in applying self-attention to abstracts, right? So we try to go sort of one step further to actually model the whole document. The self-attention a little bit unwieldy, so we actually come up with this sort of like novel neural architecture we call the multiscale representation learning. The idea is that we try to kind of decompose the whole representation learning into sort of local sort of text units and also account for actual partial relations, right? So sometimes you may not see the whole drug gene mutation even within a paragraph. You never see them in any of the paragraph, but you do see drug gene in one place and gene mutation in another place and drug mutation in yet another place. And the idea is that we can aggregate all of them to have a document level sort of like relation representation and then do all the sort of the usual learning afterwards. So in the graph LSTM work, which is a couple years ago, we showed that by doing distance supervision, we can actually bootstrap from a small set of manual curated effect and actually get orders of magnitude more from it. And the graph structure actually help, especially if those syntactic structure are actually of high quality. We then actually show that we can actually, using this deep probabilistic logic mechanism, we can effectively combine all these three major type of sort of indirect supervision into a single coherent probabilistic framework, and it actually substantially improved both the precision and the recall. And more recently in NACO, to appear in NACO, we show that you can do this multi-scale representation learning and actually further extend the gain. So for example, here what you can see, this is area under the precision recall curve, right? So the gray area is actually when you are limited to the sentence level, but once you go beyond to the paragraph level, you got the blue region as well. And if you extend to the whole document level, then you actually get to sort of the red area. So with all this sort of like progress, we actually get to a point when we already start seeing sort of like glimpse of hopes for impacting the precision medicine and healthcare in general, right? So we are very excited about this emerging area called Curation-as-a-Service, right? So here the main idea is very simple, right? So in biomedicine, you have lots of text, and they often grow very rapidly. And also there is lots of valuable information. In fact, they're so valuable that people hiring this expert to try to curate them by hand. The challenge is just that it's not very scalable, right? So the question is that can we actually speed up, make those curator superhuman, right, to curate much faster, right? So over the years, I got asked about Watson a lot, right? So in the early days, like people ask, like, there is already Watson, right? Why are you still doing this, right? And nowadays people will ask, well, even Watson having a little bit trouble, and why are you doing this, right? So when there is actually a very fundamental difference in our approach compared to Watson, right? So if you look at Watson oncology, Watson genomic, where they have done a lot of work. There is this very ambitious goal from the get-go. They try to do this end-to-end diagnosis and treatment. But when you think about it, medicine is very complicated, right? So if you put 9 oncologists on a difficult case, they might give you 10 different opinions, right? So it's very hard to come down to sort of a consensus, ground truth, and so forth, let alone label sufficient example to train the machine learning, right? So we are emphatically not trying to target those kind of end-to-end automation. We are trying to basically focus on playing faithful foot soldiers to those experts, trying to take away the boring, repetitive, most time-consuming work, but also happen to be sort of easily agreed upon, easy to get ground truth, easy to evaluate, right? So for example, in machine reading, we focus on whether the text, we take the offer at their face value, we focus on figuring out whether the text describing this relation, right? If you put 2 sort of knowledgeable, reasonable people, they will tend to agree on this part, right? There is a lot of sort of the more fun part, more harder part, like, okay, do I trust this lab's paper? Does this study have a sufficient sample size so that I will bet the patient's life on it and so forth? Those are much, much harder to automate, but those are actually sort of the tip of the pyramid, right? So hopefully when we weed out 99% of the irrelevant stuff, surface the only promising useful stuff, then they can actually go about those much more efficiently. So, and then over time, once we already provide immediate value prop to them, then they can start using it, and this would create a virtuous cycle. So for example, in the tumor board case, right, so instead of having those curators go to the PubMed and read 10, 20 pages of papers, machine reader can actually gather all those candidate facts, right, at their fingertip, and they basically look at them in context, and then very quickly they can actually decide whether this is the right thing I want to curate or not, and click a button, finish the curation. So we basically get to a point when we are working with some cancer center where the preliminary results suggest that we could probably help them, finish a whole year worth of curation probably in a few weeks, right, or faster. So that's sort of like kind of like the current state. And looking forward, there are many sort of really exciting areas. So the molecular tumor board is the more mature one, but there are also a lot of them. And actually, it's no exaggeration that many of those bullet point are billion-dollar business by themselves, right? So in molecular tumor board, for example, even you can see even the big guns like Memorial have trouble to scale to the exploding knowledge. But if you look at the U.S., 85% of the hospital are like cancer hospital are community hospital. They have even less access to those expertise and the latest information. So our aspiration ultimately is how can we level sort of the playing field, right, to enable all patients sort of get to the best of the care. But if you look at the text front, right, the literature is really just the tip of the iceberg. There is tons of text in electronic medical records, and EMR are basically in universal adoption in US thanks to the HITECH Act 10 years ago, right? So there is lots of valuable information in this, right? So for example, to publish a paper in New England Journal of Medicine, you may recruit thousands of patients, conduct a few years study, collect the statistic, and then publish a paper. But if you look at it, for example, in the US, right, less than 3% of cancer patients actually enroll in such a trial. So the rest of 97% of the patient information are still captured in the EMR, but right now we have no access to them. They are in complete silo, right? So there is this sort of somewhat odd term to us, right, called real-world evidence. It's actually a technical term in medicine and probably going to become a buzzword like precision medicine very soon. The idea is that what if we can unlock all those information in the EMR, the valuable structural information, and that could actually help us make a lot of big impacts. So for example, we are basically starting with something that are really sort of like easy and tangible to provide immediate value prop, right? So if you treat a cancer patient by law, you're required by law to report the basic cancer attributes. And right now, not surprisingly, people hire, an army of those cancer registrars to try to do this job. And they're still having months of backlog covering a fraction of the patient and so forth, right? NCI is not very happy about it, but we are basically starting some pilot project in trying to help them sort of like make this process a bit faster, try to replicate our success in the literature domain. But you don't have to stop in just basic cancer attributes, right? What if you can, in addition to that, what if you can also extract like treatment, outcomes, and so forth? You can now actually make a lot of contribution even to the oncologist's decision making. So in cancer, for example, a depressing fact is that the standard of care often don't work. In those cases, what do you do with a dying patient, right? So as an MD, you can prescribe any sort of currently approved drug, even though the drug has not been approved for the particular condition. That's why it's called off-label, right? So the problem is that when an oncologist make this kind of decision, they are based on maybe the 5 previous data points that they have seen in the past, right? What if we can actually help unlock all this kind of off-label drug use so that now they have 5,000, data points from 1,000 oncologists, right? So that will immediately be able to help oncologists. And Another sort of challenge and another sort of like best hope besides from off-label drug when the standard of care fail is to enroll the patient into a clinical trial, right? So in 2018, there were over 4,000 new clinical trials have started, right? And so how can you match patient? And each trial, for example, is described by this elaborate eligibility criteria, who should be enrolled into the trial, right? So right now, this is done completely manually by word of mouth, so not very efficient. For a patient, this could be life and death, right? So if you can find the right trial, you get saved. Otherwise, it's probably death. On the flip side of that, a lot of the trials fail simply because you cannot make this process efficient enough, right? So another area we can potentially help is that if we can parse all the EMR, right, get all those structured patient information, parse the eligibility criteria, get all those criteria, and then we can scale this matching process much more efficient. And then if you look actually at an even jump up one level, right, think about the whole drug development business, it's actually in a very scary moment, right? So an average FDA-approved drug costs, conservative estimate is that one drug costs in average more than $2.5 billion, right? And right now we approve about 50 drugs, so that's lots of billions there. And going forward with precision medicine, you actually need to approve more drugs for each of them for a smaller population. So how can we sustain this, right? And if you look at a lot of the costs, it's actually in this sort of randomized control trial in the phase 3, right? When you got a bunch of people, you give them a new drug, you got a bunch of people, you give them standard care. And then you compare the differences. Hopefully show the new drug is more effective, right? So by definition, what is standard of care? It is something that you're already practicing in the EMR, right? So then what if we can actually unlock those information and now all of a sudden you cut the cost by half, right? And so, in fact, somebody have already, showed that this is plausible, right? So there is this company called Flatiron that basically hire an army of abstractor and painstakingly curate a lot of those structured information, and they show with a pivotal study with Pfizer that this is actually indeed practical, right? And then they got acquired by Roche last year. For $2 billion, right? So, but if you look at how Flatiron operate today, right, they use minimal NLP, very shallow tool, and the curation is still not very efficient. So what if we can help them curate, speed up the curation by 10x, right? So synthetic control is basically before the drug approval, but on the flip side, there is also a huge pain after the drug approval. You actually need to monitor how well the drug actually behaves in the general market and in the general population. So it's really the flip side of things that you still need to keep track of it. And some of the phase 5 trial actually cost more than all the 1, 2, 3 combined, right? So again, overall, we can potentially play a lot of key role to help them. So obviously, as you can see, this agenda takes more than a village, right? So I'm really blessed with a growing, sort of really motivating team at Microsoft to try to tackle a tiny bit piece of this. I also personally benefit from lots of collaborator over the years with their inspiration, with collaboration and so forth. So without any of this, obviously we cannot without all of this, obviously we cannot do any of this work. So thank you, and I would like to take some questions.
Great talk. I'd be interested in learning about how the actual, in these tumor boards, they're actually using the KBs that they're seeing. So what does that interaction actually look like?
Yeah, great question. So essentially you can think about the tumor board at the first order abstraction, right? So when you get from sequencing, either from panel or whole genome sequencing exome, so you basically, at the end of the day, you get a list of gene mutations, right? And then the KB you can think about at the very first order approximation is just a table with drug, the dimension there, maybe extend with cancer types and so forth, right? So it's actually a trivial sort of database join. You basically say, for this set of gene mutation, here are what we know. And so today, basically, like there are places like Foundation One and so forth that offer this kind of service. One challenge is that they focus on a very small set of genes, like 400 out of 20,000. Secondly, the knowledge base is by manual curation. So oftentimes you see those reports, they could not give you actually actionable hits. So our hope is to unlock all those knowledge in the literature so that they don't have sort of missed facts as step one. Yeah. Thanks.
Thank you. Very interesting work. How can we represent the additional constraints or circumstances under which a relationship is true? Because the schemas are usually very rudimentary. They don't capture all the context.
Yep. Great question. So every time I go to a bio conference, they will say, hey, this fact may not be true in this context and that context. So again, if you think about that curation pyramid, what we are looking at, right? So we basically take sequential 80-20 approach, right? So we first, for example, for the tumor board, drug gene mutation are sort of arguably the biggest 80-20 things, right? So we focus on getting it correctly. So for example, we make some joke with the curator, like, okay, you can probably have a lot of beach time now, right? But they basically push back exactly with that, like saying, hey, we have actually a long list of things. I need you to help with, like, for example, obviously, what's the cancer type, right? How big is, what is the trial, right? Is it a human, mice, xenograft, cell lines, and so forth, right? And also, what's the sample size, and also, so we can basically think about framing additional machine reading tasks to get exposed more and more those key attributes in a sequentially sort of 80-20 rule. But right now, we basically reserve the final fund for them to say, okay, at Memorial, we do it this way. At MDA, we do it that way, and so forth. Those we leave for them to decide. We're just exposing those structural information.
So are you saying that the curators actually need to add these attributes to the knowledge base?
Well, so basically, like what you can see early on is like, so for example, in the drug gene mutation, right? So the machine reader already get them, right? So now tomorrow, if we have several new attributes, we can expand our machine reading scope to get them, and so you can see this going more and more, right?
Thank you.
If there are no more questions, let's thank Hoifung again.
Thank you.